All right, sorry for that slow start. So I am working, so I've gotten through about half of your input modeling reports. And so some of you will have feedback, annotations on the report. There's also annotations within the rubric, each section of the rubric, as well as comments. So make sure to check those. Hopefully I'll get through the other half today. So far, no major red flags, just kind of the common things about confusing inputs and outputs and making sure that we're trying to address kind of a problem that is interesting enough. And so there's a lot of questions like people said, well, can adding an additional cashier improve performance? Well, we kind of already know that it will, but then the answer really would be, could I estimate what the performance increase could be and compare that to, say, the cost of that intervention, adding the other cashier, and seeing if it's worth it. That starts getting to the point where it starts becoming a more interesting question. And so these sorts of to what extent or how much of an effect, those are sort of more kind of simulation worthy questions to answer things that we don't really know ahead of time. Or if your intervention is kind of multi-dimensional, like I could do X, I could do Y, I could do Z, or I could do a mixture of those three to improve operations, trying to understand, well, X has a much bigger bang for the buck than Z. So maybe if you have a finite budget, you focus on X. Like that's something that would also be sort of like an interesting thing. So these are kind of abstract comments, but inside the input modeling report comments on Canvas, I tried to make sort of more specific comments that they're tailored to each one of yours. And so, like I said, I've gone through about half of them. So I've got the other half to do. And so hopefully I'll get those done today so that you'll have that feedback back to you. Otherwise, we're doing the Lab 9 Output Analyzer lab today. So introducing, or not today, this week, introducing another tool that Arena comes packaged with, similar to the Input Analyzer, but where the Output Analyzer takes data from Arena and then gives you some statistical tools that you can use with it. For your final project, you could also export data in another format and bring it into JMP or R or SAS or whatever tool that you're, or SPSS that you're more familiar with using. But at least for this lab, want to give you some exposure to the output analyzer that comes packaged with Arena. And then Lab 10, Advanced Topics. Again, this is sort of a lab that it's almost like two labs in one. So it's only graded out of 30 points, but 50 points are possible. So it's an opportunity to get a bunch of lab extra credit if you'd like to get that. It adds in a bunch of other topics that I think could be useful to a lot of final projects that we didn't want to build a whole nother lab for. And so kind of packaged them all into Lab 10. With the drop 2 policy and the fact that there's so much bonus here, you can kind of cherry pick what parts of Lab 10 you want to do at this point. But potentially it at least gives you some exposure to a bunch of interesting elements that I think could be used for your final project. And then the other 2 weeks left in the semester, there's no formal lab. It's just left for your final project. So once you get that feedback from me, I mean, you can keep working even before that feedback. Then your next deliverables will be the last week of class. The Wednesday of the last week of class, your presentation video and your final report will be due that night. And it's really due, there's no grace period on that. It's due at like 11:59 that night, because then Canvas will automatically randomly assign presentations and reports for peer review. So they really have to be turned in at 11:59 because at midnight, Canvas is going to do that random assignment. And then you'll have that Thursday, Friday, and Saturday to watch your one assigned presentation and read your one assigned report and give them peer reviews, so that I can then take those peer reviews into account when I grade these for during the finals week. Other assignments, there's ICAs, there's one ICA J3 and then ICA L after that. The only other ICAs are the final exam ICA. Homework J2 should be out there and available. That is an Arena-based homework. And so we have used this homework in the past to capture some ABET metrics, which is why a solution set won't be given, but this is this is the inventory model system with Bucky that you've seen before. You're asked to make a few modifications to it and then do a little bit of an optimization type analysis, like you might imagine doing for your final project. and then give us the output of that. And so it's less about a practice, a specific thing, and this is really kind of a culminating homework where you're bringing a bunch of stuff together with Arena into one homework. So any questions about the administration going forward? Okay. All right, so let's start with a attendance question, just to get everybody warmed up. And so the question here is, the student's t-test is one of what's called a location test. So assuming the data are normally distributed, it only evaluates the probability of a particular location parameter. So in this case, mean. The mean is the location parameter. And so it's evaluating the probability of a parameter. Because it evaluates the plausibility of parameters of a distribution that are taken for granted otherwise, the t-test is an example of what kind of test. So I'm looking for a 1 or 2 word answer. So that's what the attendance question is here, is what is the type of test that a t-test fits into? It is a location test, that's one thing, but that's not what I'm looking for. The type of statistical test that takes a distribution for granted so that its inference is only on a parameter is called what type of test? I'm looking for there. All right, so think about that for a second. So what's the answer to this? Anybody have a guess? There are 2 major types of statistical tests, this test and a non-this test. Yeah, parametric, that's what I'm looking for. So the answer to this attendance question, which are not graded for correctness, or just graded for coherence, is a parametric test. And so, so if I were to go to Wikipedia, I forget where I found this table, but I was happy to see somebody had put this together. This is a table of parametric and non-parametric location tests up here. And so these are a bunch of location tests. And you can see that they group them in, again, parametric and non-parametric. And so there's kind of a decision tree here that they've built out where they said, well, if you only have one group that you're worried about here, if you have a large sample size for that one group, then they can say you can use a 1 sample t-test. If you have a smaller sample size, then you have to really check to see if it's normally distributed. And then it's probably pretty safe to do a 1 sample t-test. Some would argue you should do this, check to see if it's normally distributed for this one. But usually if they're higher than 30, then things will just very often be normally distributed. But alternatively, if it's not normal, then they say to do a sign test. And so this is where you can see, I said there's like non-parametric versions of t-tests, and this, it's written as a table, but this kind of decision tree at the leaves ends up having the kind of like the parametric test you've heard about from, say, 380 or 385, and then maybe the non-parametric test you haven't heard about but is applied the same way. So, and then the same thing down here for chi-squared test, Fisher's exact test, et cetera. So as you start doing stats professionally, these will be very helpful tools, or just being able to know what to Google, like, what is the non-parametric ANOVA, and so I know that for an ANOVA, that's 3 or more groups. So for 3 or more groups, if it was normally distributed, I would do my ANOVA that I learned about. Or I might do a 2 another if there's greater than 2 factors. But if it was not normally distributed, Kruskal-Wallis. And so the KW test is what I do there. So if I were just to Google for non-parametric ANOVA, I'd find that. Over time, you start embedding this type of decision tree in your head, and you start remembering, which one is which. And so there's like a huge taxonomy of statistical tests that are not out there just to be competitors to each other. They're out there because of all of these different conditions. And so to make the math of p-values work, you have to make certain assumptions. And when you can't make those assumptions, you can still calculate p-values, but you lose statistical power. So to have the most high-powered test with a p-value that actually means something, then you have to go through this kind of process here to make sure you pick that. Sure, you could always do a non-parametric. You could pretty much always apply a sign test or always apply a Mann-Whitney U test. But the downside of that is if you need statistical power, it would be better for you to apply the other tests. If you're just trying to reject something and that's a good enough result and you actually don't really care about the other side of that, then maybe you do just apply the non-parametric. But so it's kind of like whenever possible, apply the parametric test. But when the parametric test is not possible, there are fallbacks, and that's kind of what's being encoded here. So that's just, again, I'm going to test you in this class on whether you know all of these different types of tests. But I do want you to be aware that that things like the t-test, the ANOVA, et cetera, are valuable and you will use them in the real world. But I also want you to know that there are a bunch of other tests, and once you learn how to use a couple of the basic parametric tests, the rest are just kind of like, they allow you to do the exact same thing just when the assumptions don't hold. And so you can import all of your intuition from your parametric tests into figuring out that you need these other tests. And so it shouldn't be necessarily intimidating that all these other tests exist, because all these other tests kind of naturally fall into play as the kind of fallbacks when the test, your favorite test, doesn't work or can't be applied. All right, so any questions about that stuff? About this general framework? All right. Okay, so Unit J, where we're starting here, we are interested in finally looking at the outputs of simulations. So what outputs do we look at? What sort of statistics do we use? How do we trade off computational time and statistical power? So how many replications do we run of these simulations in order to make a convincing argument, trading off computational time and bias reduction? We're going to learn about certain types of simulations that tend to have biased outputs, and you can dump extra computational time into reducing bias, but you don't get any good data out of that time. And so there's also a trade-off there about at what point have I reduced my bias enough to when I can actually start taking useful data. So these are kind of the three big points that we're focusing on in this unit. And this unit starts here with us talking about two types of systems, terminating and non-terminating, which are simulated by two types of models, transient simulations and steady state simulations. So let's get started there. A terminating system is a system, so think about the real world here, where it is truly meaningful in the real world that there is a real end time. So we care about the end time in the real world. So it's like we are simulating a bank that opens at 8 a.m. and it closes at 6 p.m. and we want to simulate the whole day of the bank. And we really care that it's opening and closing. It has an end time. So the end time exists in the real world. That's what I mean by a terminating system. This could be a length of time, or it could be until some condition is met. The bank is open until 6 p.m. or the last customer who came in before 6 p.m. is serviced. So the bank might close a little bit later than 6 p.m., but it's, it's that condition. So as soon as we've cleared all the customers who came in before 6 p.m., then we stop the system. But the stopping is real. It's something that we don't impose artificially in simulation. In the real system, there is a true thing of a stopping time. And that's what we're saying is a terminating system. And terminating systems are simulated by what we call transient simulations. So I call them transient simulations for reasons that will become more clear as we go on, where it's because I care about the transients that occur right after I start the simulation. So I start the simulation and there's always a warm-up period in every sim. And the question is whether that warm-up period is just an artifact of the computer or of the model that I built, or if it's modeling something in reality. In reality, there's also a transient, and so I am simulating that transient of what happens right after start up until whenever it ends. And that's why we call these transient simulations. We're going to learn that the other type of simulation, a steady state simulation, we get rid of the transients and only focus on data after they've died out. And that's why it's kind of like, maybe I should present steady state simulations first and then use transients to contrast against them. So like I said, the bank is one example here, opens at a particular time. Maybe no customers are present when they're open. So, and 8 of the 11 tellers are working. And so it closes at a particular time. So it opens and the initial conditions matter. So initially the bank is empty. And so in my sim, initially my bank should be empty. And that's just not a convenience because Arena starts everything empty. That's the reality. So I actually care about the ramp up as people enter the bank. So that's what I'm actually simulating the transient. So I model the bank as the terminating system, and I focus on that 1 day's operation. And so another example in Arena here is a call center that stays open long enough to clear the queue. That's an example where I have down here a terminating condition. So let me see if I can see if this works. I thought I had it. Oh, well. Okay, so I was trying that was not what I wanted to do. I apologize for that, and I'll reshare. All right, well, I'll just use the mouse. So in the call center example that we gave in lab, I forget how long ago that was, there's was a pretty complicated call center here where it opened a particular time, they started taking calls, and then the call center closed, but they couldn't actually stop the sim until everyone was out of the queue. Well, if you go into Arena's run setup, then you could, up until this point, we've pretty much always set the replication length to a finite duration up here. So replication length infinite there, or to a finite there. But alternatively, we can set replication length to infinite, and then instead fill out this terminating condition down here where it says t now is greater than or equal to 600. In this case, it looks like base time units minutes. And this in R trunk line is equal to 0. This basically means the number of callers waiting in the trunk line queue is equal to 0. So at the point at which we've reached 600 minutes and no one else is left in the queue, then we terminate the sim at whatever t now that might be. That could be a t now equal to 900 or 950 or 614, or if it happens to be the queue is empty, right at t now is equal to 600, it'll end right at 600. So inside Arena, we can actually have flexible termination times. It doesn't have to be terminating at a specific time. And then we can even study, how long do our simulations normally run? That could be an output variable. So we would like to organize things so people actually get out of here on time. And you could say, that might just mean reducing queue lengths, so there's less people waiting right when the 600 minutes happens. But you could say, but I really want to make sure this is actually working, so I'm actually going to measure what time everyone stops working, and you could then record the t now right at the end of the simulation. So that could be an output you gather. All right, so questions about that terminating systems so far. We're going to contrast them with non-terminating. Okay, so let's see non-terminating. Let's use this as a contrast here. So a non-terminating system is a system in the real world that does not have a start time or an end time that we care about. So an example of this might be a 24/7 Walmart or something like that. That Walmart once opened and it will occasionally close. But those are such rare events that we as operations researchers don't care about them. We are not going to build a strategy for running Walmart just based on the rare times it opens and it closes. For our models, we assume that Walmart is open forever. And so that is what we mean by a non-terminating system. For the purposes of studying the operations, it never opens, it never closes, it's always running. It is non-terminating. And so we study the long-term properties, or the so-called steady state properties of the system. These are properties that are not influenced by the initial conditions. So it's true that Walmart had to close one time. Maybe there was a a natural disaster or something like that, and they had to reopen it. And when they reopened it, it took a while for all the lights to turn on. It took a while for all the employees to arrive, for customers to realize they're open again. It took, and maybe their initial conditions matter. Like maybe they originally had a low inventory. So it took maybe even a week for them to figure out their inventory stuff. But then that week was an atypical week. Every week after that kind of looked like every week after that. But that one initial week, that was kind of a junk week that we kind of like, it was like a mulligan, it was a gimme. It's like, we'll allow you to do whatever that week because you're just getting stuff figured out again. This is not a normal week. And so that's kind of the type of system we're focusing on, where initial conditions matter, but for the part that we as operations research care about, we do not care about those initial conditions, and that we're assuming the system is not influenced by those initial conditions at all. And so we do need a final time in our simulation, because our simulation can't run forever, but it's totally artificial. So in the terminating simulation, we had to come up with a final time that actually corresponded to something in the real world. In the non-terminating system, this is kind of like that first homework you did with the hand simulation, where I just said, set the stopping time to 30 minutes. Wasn't 30 minutes because something happened in the real world, like the store closed in 30 minutes. It was 30 minutes because 30 minutes was enough for us to do our stats. And so likewise here, we have to have a end time that is long enough for us to gather enough stats from the sim to get a good picture of the steady state properties. But it doesn't have to be forever. So if really, after you throw away the first week and focus on the second week, third week, or whatever, eventually once you get, say, 10 weeks of data, if you average over that, then you're gonna have a good picture of what every other week is gonna look like after that. So really, as long as I have week 2 through week 10, then that's all I need. I don't really, the extra data just reduces my confidence intervals, but it doesn't actually give me a lot more help. So that's kind of the type of system that we're working on here. So we, as simulation engineers, have to figure out how long to run the simulation in order to get that kind of statistical convergence. And that might be a large number, but we don't want it to be so large of a number because it will end up just running forever. And so we'd like to make it as small of a simulation as possible that still reaches this kind of statistical convergence. So examples of this are like assembly lines that shut down very rarely, telephone systems that are open 24/7, hospital emergency rooms are a great example of this, 24-hour grocery stores, Walmarts, et cetera. These are all types of systems that they do periodically shut down and open up. We don't care about that as operations researchers. We are developing policies for the steady state. So any questions about that distinction? Does that make sense? And so I can summarize those in the picture. So I've got my terminating system with my transient simulation on the left here. There's a natural start of system operation over here, maybe over. There's a natural start over here, down here. There is a natural end at some point over here, and all of the data in between are good data. So we actually care about this ramp up because this ramp up happens every single day the bank opens. And so whatever we can do to improve that ramp up or change things in that ramp up is actually a real thing we can do in the real system that we will really care about every single day. We contrast that with a non-terminating system where there is a ramp up in our sim, and there is a ramp up the few times that Walmart shuts down and has to reopen. There is a ramp up inside the Walmart as well. And if for some reason Walmart changed their business model to where they opened and closed every single day and weren't 24/7, then we would start caring about that ramp up, and we might have to start shifting them into thinking of them as in transient simulation terms. But normally, we're focusing on the steady state behavior, not that ramp up. So our sim is going to have a ramp up, and we are going to put that into what's called a warm-up period that we truncate that. Our sim generates data, but we discard all of that data. And so we can go into Arena and we can say there is a 2-hour warm-up period. During that period, do not take any stats. Just let the simulation run, but your first stat should happen at 2 hours, not at 0 hours. And so that's what I'm kind of showing here. So then we have this good data that's right here, and then we have some end time, which is artificial. It's just when we decide to end the simulation. Now note that if we end up not discarding this data, and we're trying to estimate, say, the steady state average here. So let's say we're trying to estimate what we would ideally like to estimate is kind of the middle point here, the kind of average over time of this steady state curve here. We'd like to average where my hand is here. If we include too much of this transient and average over this entire time period, then our estimated parameter is going to be low because it's including this junk data. So if we accidentally include too much of the warm-up period, we are going to create a bias in our estimate where the real world steady state value will be up here, but our reported steady state value will be lower than that. And that's what we need to eliminate bias. And one way to eliminate bias is to make this warm-up period as long as we can tolerate, because we're kind of guaranteed then to get rid of these transients. But the longer you make this on a finite simulation budget, you end up compressing the amount of time you have left over here, so you lose out on some of that statistical certainty. So we need to somehow gather as much data we can in the steady state while throwing away as much data as we can in the transient. Right, so that's kind of the key difference between terminating systems, which are simulated with transient simulations, transient because we include the data, versus non-terminating systems, which are simulated with steady state simulations. And these are steady state simulations because we do everything we can to discard this data. So we only focus on the steady state. Any questions about that distinction or those terms? Questions online? All right. All right, so I'll skip this for now. All right, so let's, so just to put that framework in mind, so like where do we get sources of variation in our simulations? And how does this affect gathering stats, thinking about terminating and non-terminating systems and all of that? So I've got an example here where I have got what I'm referring to as a batched output from 3 simulation runs. So what I've got here is I have 3 simulation runs that are represented by the columns. And when I refer to, it's unfortunate we use the term batch, but it's just one of these things where we have batching in kind of inventory management sort of stuff. We also have batching in terms of simulations. So these batches are sort of batches of time. And so I'm saying that I have a 5,000 minute simulation that I'm going to cut up into 5 batches. The first batch from 0 to 1,000, second 1,000, 2,000, and so on. So I do have the whole time series for each replication from 0 to 5,000, but I also, for each replication, have cut it up into these 5 batches. And I use this term replication. Those refer to the 3 independent simulation runs. So I go into Arena, I hit run, and it generates these data. And then if I set it to do 3 replications, it will then rerun, and it'll generate these. And then it'll rerun, and it'll generate these. Okay, so I have 5 batches per each replication here. So I can analyze the stats per batch, and I can also analyze the stats per replication. So the stats per batch give me what I might refer to as within replication data. So inside this one replication, I've got data points taken from the early batch, the slightly later batch, and so on. I also have so-called across-replication data. So from replication 1 to 2 to 3, I have different data. There's variation within the replication as well as across the replications. And when there's variation, we have to use statistics to understand it. And there's different statistics we can use, primarily because across replications, these data are guaranteed to be independent, which means they're good for t-tests and things. Within replication, these are not guaranteed to be independent. And so early in the system will probably affect things slightly later in the system. So going from batch 1 to batch 2 within replication 1, that's probably, these 2 numbers might not be independent from each other. In other words, if I know that it was 3.6 in batch 1, I might know that it's unlikely to be anything higher than 4 in batch 2. So if this is like an inventory shortage or something like that, I know it takes a certain amount of time for me to get more inventory, then I know that there's going to be kind of some inertia here where the inventory in batch 1 is going to be related to the inventory of batch 2 and so on and so forth. So within replication, I have lose independence. Across replication, I get independence because we use different random number generators, or we use different random number seeds. So, so that's what I want you to sort of picture here is I've got within replication variation and across replication variation. All right, any questions about this general example here? Because I'll kind of be referring back to this general idea that we're going to have data points that we average across replication, or we have data points that we average across a batch and then view all those batches within a replication. And these batches could also be of size 1, in which case this would be a single data point, and then another data point right after it, and so on. But we could imagine making these batches larger, and then we're kind of averaging across these batches. In general, when you run one giant long replication of ARENA, it tries its best to create intelligent batches so that it can try to estimate across replication variables using within replication data. So ARENA will do that for you automatically, but as long as your replications are long enough. And that's its way of sort of assuming that if these batches are long enough, then maybe this batch will then start becoming independent from this batch. And we're going to talk about that case later on with steady state. So ARENA will automatically try to do that for you. That's how, when you run one replication of ARENA, it still gives you confidence intervals. You're like, how could I get a confidence interval? I've only had one replication. And that's because it generates fake replications from these batches. All right, so our objective is to estimate a performance, system performance with our simulation. These performance measures can vary. So we are going to need to create an estimator, and we were going to start with point estimators that we've been talking about here. So our point estimator is very often just an arithmetic mean. And so I can take a bunch of data points. So I could go here and I can say, well, if I've got a data point for replication 1, replication 2, replication 3, I can average all those together, and the sample mean will be a point estimator of whatever performance variable this is, like average wait time. And so if I do have independent data points that I'm averaging here, then I am allowed to generate what's a standard error of the mean. So in other words, if across replication data, these are independent, and so I can not only average these together, but I can also estimate what is the standard error of the point estimator. That's what the standard error of the mean is. And so this tells me the variance in the estimates. In other words, if I ran another 3 replications and created a new average, it would differ from my previous average. And this would tell me an estimate of the standard deviation of that sampling distribution. And so I can also, so how do I generate the standard error? I do that by estimating the variance across the points that I have and dividing by the square root of n. So this is an important formula, s divided by the square root of n. That's why we see it in the t-test. So we can see here, as the number of observations increases, the standard error collapses to 0. And so if I ran 1,000,000 independent replications, then I am probably going to get a highly confident estimate of the average of this performance variable across these independent reps. All right, so standard error of the mean and our point estimator. Now, as I said, each run of a simulation we're calling a replication. I'm going to often use capital R to represent the number of replications. Across replication data are independent, identically distributed, and often normally distributed because they're often themselves generated by summing processes. So the central limit theorem often really helps us with these across replication. So because of that, across replication data, I can usually use things like t-tests and ANOVAs for, because they meet all of the assumptions of that. So if I want to say, I want to test a hypothesis that, this, what's the I'm going to test the hypothesis that these performance variables coming across replication data come from a population whose mean is 3. Well, I could test that hypothesis by throwing these data into a t-test where the null hypothesis has a mean of 3. So the mu in the t-test is a 3, and the average of these is the y hat. And I throw that in, and I generate a t-statistic. And I'm allowed to do that because these generally are going to be normally distributed and independent. So that's the case for these across replication. Within replication data, I have far fewer tools that I can use. Within replication data, I have autocorrelation. So the earlier batch may correlate with the later batch, and so on. And so because I don't have that independence, so here I've got this, the inventory cost for the ith week, well, if I consider that as my yi, then for the I+1 week, that inventory cost is likely still correlated. So if I was paying for, putting, I had whatever, 20 Twinkies on a shelf in 1 week, and the next week I probably still have close to 20 Twinkies on the shelf. And so whatever it cost me to keep them on the shelf in week 1, it's probably going to cost me similar to that in week 2. So there's natural autocorrelation across time. And so that means that's a violation of statistical independence. So I can't even use the standard error of the mean formula. So if somebody asks you for an estimate of some data that has autocorrelation, and they say, oh, and can you put standard error bars on that? You might have to say, no, I can't actually, because those standard error bars actually don't tell you anything, because standard error bars are, at least this formula is only defined when the data are independent. So it's within replication data, there's not a whole lot I can do with them. The other thing that I have to worry about within replication data is this bias effect, the effect of initial conditions. So if I imagine, so say simulations initialize variables to 0, like this is just often the case. Usually when you start your sim, no one's in the queue. You can go into Arena and make it so that you start out with people in the queue, but that's like a bunch of extra work. So normally you start out and no one's in the queue. Well, that means that initially, if you're measuring average queue length or something like that, if you include that hour of the beginning of your simulation as people start ramping up in the queue, then you're going to have a biased estimate of the queue length because it's going to include this fictitious period where no one's in the queue just because you're starting the sim with an empty queue just because it was convenient. So the point estimate ends up being what we call biased. And so we'll formally define how we measure bias here in a bit here. But that's another major problem we have within replication data is the effect of the initial conditions. All right, so other things that, so we'll get to bias and things like that. So other estimators that we use here. So I mentioned that we use the mean as our common point estimator. The other really common point estimator are quantiles and percentiles. So, as an example of that, somebody might not care about the average. They might care about what's the 85th percentile value. So as an example, when you drive speed limits, for example, speed limits are set to be the 85th percentile speed. And so they know that people aren't going to drive the speed limit, but they want 85% of the people to drive that speed or less. And so if you're evaluating whether you've properly set enforcement on roads, you look for what is the 85th percentile speed that we observe on the road. And if that matches the speed limit, then you've got the speed limit set correctly and you've got the enforcement strategy set correctly. Same sort of thing with sims. You could get a bunch of data out of it. Rather than taking the mean, someone could ask, well, what's the 85th percentile queue length or something like that? So this is the queue length that 85% of the time you're less than that. We recognize that sometimes you got to go over it, but we want to at least know 85% of the time you're going to be less than that. Or what's the 99 percentile queue length? This sort of gets closer to thinking about quality control, and Six Sigma and all of that. Six Sigma is all about not the mean, it's really about the tails of that distribution. And this allows you to get into those tails. So you're often asked to estimate the quantiles or the percentiles. The other estimator that we're going to spend a lot of time on for the rest of the semester is interval estimators. So we are going to introduce confidence intervals here, and we are going to do our best to, whenever we get an opportunity to estimate a value, we are going to use an interval estimator, and we'll define what those interval estimators mean. And so, like a confidence interval, which you've seen before, which we'll define a little more rigorously here, gives you not only the mean, but it gives you how confident you think the true mean is close to the estimated mean. Because your estimated mean is just the mean of the data you gathered. It is not necessarily the mean of the population, but it might be close to the mean of the population. And the confidence interval tells us how close do we think the mean of the population is to the mean we got from the data. And prediction intervals, which is a measure of risk, is given that you've given someone a mean, they might still be interested in knowing, well, what's the spread of values I might expect if the system were to run once more. And so that, if you just ask for one replication, that could be very far from the mean. So I can give them a prediction interval to say, well, generally, the values that come out of the system are around this average. But it's possible that sometimes they get this high, sometimes they get this low. And the prediction interval kind of gives you a spread of the possible values that could come out of the next run of the system, of the next iteration of a system. And so we'll define how to write these two intervals here in a second. All right, so any questions so far on kind of the motivations behind this? With the deal with these different types of data, across replication, we have a bunch of statistical tools. Within replication, it's a little more troublesome, and so we have to handle them specially. And we're either going to be estimating points, means and quantiles, or intervals, which give us confidence about the population. All right, so I mentioned bias before. This is how we define bias. And so we're estimating some value theta that's in the real population. So this is like the true average length of a queue. And we then generate a bunch of samples from our simulation. So they have over 10 replications. This is what the average queue length was for each replication. And that allows us to come up with a theta hat, which is our estimate of the true average queue length. But it's just an estimate. And so the mean value of theta hat minus the true value of theta, that is what we refer to as the bias. And so if we are to generate theta hat over and over again across different simulation experiments, that gives us a mean. And we would like that to be exactly equal to the real population mean, but it may not be. So due to those initial conditions and things like that, we might generate bias. And so we would like the expected value of our simulation estimator to truly be the real one, but it may not be. And so that's bias. And so this was the example I gave earlier. So if I include too much data, then these initial transients in a steady state average are going to push down the estimated time in system so that it's going to be biased. But if I throw out these data, then that shifts would end up shifting the estimate up. And so if I'm throwing out the data, I am trying to make my estimated time in system match the true steady state time in system. Okay, so any questions about this idea of bias and how this, including these data in a steady state simulation, generates bias? That's what I'm trying to show here. And we define bias by saying it's the estimated value that comes out, the average value that comes out of running simulations compared to the true value in the population. And we can show sometimes mathematically when we have an estimator that has bias and when it doesn't. Other times we have to kind of look for a convergence. So you could imagine I'm going to run 10 replications without discarding any data. I'll run 10 replications discarding a little data, 10 replications discarding a lot of data, and so on. And as I start discarding more and more data, I get a convergence in my estimates. And I should assume that convergence is converging to the population mean. That's one way I can try to reduce this bias. Okay, so the different estimators we use, usually we use means. because most of the things you're going to gather are going to be discrete time. So you'll be, or there'll be a cross-replication. So you have a discrete number of replications, or you have a discrete number of times within a replication. Occasionally, within replication data, we integrate over time. So there are going to be these continuous time variables, and that's like at any instant of time, I could ask how many people are in the queue. That's not something that's a discrete time. That is, I really could ask it really at any instant, right now, at this instant, who's in the queue. And so that gives me a discrete time variable. And that discrete time variable, I can then integrate the area underneath the curve, divide it by the time interval, and that's how I get a time average. So this is what we mean by a time average, is it's an integral divided by an interval. So the length of the interval, and then I integrate over that length of the interval. So I've got examples here where, whether we, this is discrete time data where I've got whether I'm on day 1 versus day 0, are we out of stock or not? And so today we're out of stock, tomorrow we're not. So it's a 1 or 0, and but it's indexed by day I, versus the continuous time case where I can say here, are we in an emergency condition because the length of the queue is greater than 10, or we're not? Well, this I can ask at every instant. This exists at a day, this exists at every instant. So there's my discrete time and continuous time examples. Any questions about this? I know some people had some questions on the ICA about discrete time versus continuous time. So hopefully this example helps with some of that. It's not about the value of the variable, it's about the time at which the variable is defined. Okay. All right, then quantiles. So the inverse CDF of any distribution is also called the quantile function. So what a quantile is this is a value, theta, for which the probability that all other values are less than that value is equal to whatever that quantile is that they've asked for. So if I'm saying, like, I'm asking for the 85th percentile or the 0.85 quantile, then what I'm asking for is what's the value of theta for which the CDF, that's what this is here, happens to be equal to 0.85. So if you have the CDF, you can calculate the quantiles. So, so that's how we define quantiles. Now, how do we generate quantiles? And by the way, the median, for example, is the 50th percentile. The median is the 0.5 quantile. So that's kind of a special quantile there. So they might ask, what's the median queue length? Well, that'd be the same thing as saying, what's the 50th percentile queue length? To estimate these quantiles, I take all my data and I sort them. This is a common thing we end up doing. And then I just find the value that's sort of at the right position. So the P quantile is the one where if I say I have n data points, we'll multiply that by P. And that says, okay, if it was 50%, if I'm looking for the median, then I just take n divided by 2. And then I end up rounding that up to the next index, so the next integer, that value there, the next whole number value, and that ends up being my estimate of the quantile. So that's how we estimate quantiles. Just sort and grab the one in the right position. Okay. So I mentioned as an example for speed distributions. So if I'm running a simulation like this, for example, I again assume that speed limits reflect the 85th percentile. And so let's say I build a simulation, a traffic simulator of, I don't know, a freeway, and I simulate different enforcement strategies. And then I ask, using, I might use models of human behavior on each individual car. So this might be an agent-based model. You could use this probably as a DES model as well. And based on my enforcement strategies, how often I show signs, for example, how often cops show up on the road, those sorts of things, I, from my simulation, am going to see different distributions of speed. So I can say across all my cars, what's my distribution of speeds at any particular instant, or I could average over time or whatever. And so that ends up coming out of that. I get a distribution of speeds across these cars. And then rather than taking the mean speed, I might then sort all of those and then go to the 85th percentile position in the list and then estimate from this simulation, the 85th percentile speed was 65 miles per hour. And if that matched my speed limit of 65 miles per hour, then I'd say that my simulation, I've shown that I've demonstrated an enforcement strategy that, if in the real world and in my sim before my enforcement strategy, it was 80 miles per hour, and I've now added an enforcement strategy that brought it down to 65, then I've now demonstrated in sim that this might be a good enforcement strategy to put in the real world. But the people designing these things don't care about the mean speed, they care about the 85th percentile speed. So that's an example of a point estimate that is not the mean that your stakeholders might be interested in. Again, same with quality control. You don't really care about the mean failure rate or something like that. You really care about what fraction of all of the things that I put together end up having a catastrophic failure and not being able to be shipped. And I want that to be really small. So it's that, it's about the tails of the distribution or the whole distribution and not just the center of gravity of the distribution. All right, so any questions about any of this stuff? A lot of definitions before we get into actually defining confidence intervals and using them. Questions online? All right. Okay, so confidence intervals. So we've been talking about point estimates. Like I said, for the rest of the semester, we're going to transition into everything is going to be about confidence intervals. So we're going to get rid of point estimates whenever possible and use confidence intervals. So what the heck is a confidence interval? What really is a confidence interval? Confidence interval is defined as it's centered on the mean. So I take a bunch of data, I take the sample mean, confidence interval is centered on the sample mean, y hat. Now, the width of the confidence interval, we're going to call the half width. So if you see HW or just H, that's our half width of a confidence interval. So that's kind of going to be our abbreviation for the rest of the semester. If I say, give me the HW or whatever, that, or even just the H, that's the half width of the confidence interval. It's just the half of the interval. And so the half width of the confidence interval, that is defined by this formula down here, where it is the critical t value at alpha divided by 2 with the number of samples minus 1 times the standard error of the mean. And so where does this come from here? Well, what the confidence interval is it is the set of hypotheses that cannot be rejected by a t-test at alpha confidence interval. So just think about that a little longer. So it's like, so for these data, if I were to generate a t-test, a one sample t-test, testing this data against a bunch of hypothetical ideas, those numbers, there's going to be a range of numbers for which the t-test will not reject that hypothesis. So I have a bunch of data, they look like they're clustered around 0. And so if I test them against 0, I get a p of 0.1 or something like that. So I don't reject 0. I could also test 0.1 and I get a p value of 0.25 or something like that. So I don't reject 0.1. And then I do 0.2 and I try to test it, 0.2 with a t-test and I end up, again, not rejecting. And so there's these numbers, 0, 0.1, 0.2, none of them got rejected. Eventually I get out to 1. And if I test 1 against these data with a t-test, I reject 1. So 1 is a hypothesis that's rejected by the t-test. Confidence interval are all the hypotheses that are not rejected by the t-test. And so that's actually where this formula comes from. And so somebody turned on their microphone there. Is there a question online? If not, I'll mute. So that's where this term comes from. If you were to write the formula for the t-test out and then represent whether you're in a reject condition or a not reject condition, and then sort of figure out like, all right, well then how do I write the hypotheses that are not rejected, you would come up with this formula right here. So this is just a rearrangement of the t-test formula to represent that this interval are all the hypotheses that are not rejected by the confidence interval. So when we refer to a 95% confidence interval, that 95% is 1 minus alpha. So alpha is our false positive rate, right? It's our type 1 error. 1 minus alpha is the true negative rate of the t-test. So the 95% confidence interval, that 95%, that percent that you hear there is announcing this is the interval that has a true negative rate of 95%. Or put another way, this is the interval that has a false positive rate of 5%. And so that's what the interval is. It is, every time you've seen a confidence interval, it is a visualization of a t-test. The most of the world out there either has never heard of a t-test or thought it left t-tests behind when they were in undergrad. But they probably have heard of confidence intervals. Every time you hear somebody on the news or wherever say a confidence interval, they are talking about t-tests, even though they don't say the word t-test. That's where confidence intervals come from. They are t-tests. They are hypotheses that cannot be rejected by a t-test. Questions about that? Any questions online about that? Okay. All right, so one of the cool things I can do is if I do give you a half width, I can estimate a bunch of things from it. And so under sort of assumptions that the data are normally distributed, which I have in order for, so that's one thing I guess I want to make a point here, which is why I guess I highlighted it, is that you cannot use a confidence interval unless the data are normally distributed and independent, because confidence intervals are t-tests. You cannot use t-tests unless your data are normally distributed and independent. And because confidence intervals are t-tests, even though we don't call them that, we can't use confidence intervals unless the underlying data are normally distributed and independent. If we assume that they're normally distributed and independent and somebody gives us a half-width, then we can back out a lot of cool things. So we know the half-width formula here. So with the half-width formula, I can then approximate the standard deviation of that normal distribution just by rewriting the half-width formula. And I can even estimate quantiles here because I assume the data are normally distributed. If I know an estimate of the mean, that's the middle of the confidence interval, and I know an estimate of the standard deviation, that's the half-width of the confidence interval with some scaling, then I can basically put that into a normal and say, well, what would a normal distribution look like with this mean and this standard deviation? And I can pretend like that normal distribution is the distribution of all these values, and then I can calculate quantiles and things like that. So if you give me a half-width, I can construct for you a plausible distribution for that data under the assumption that the data are normally distributed. So that's one of the cool things that I can do with confidence intervals. More powerful thing that I can do for confidence intervals is estimate the outcome of two sample t-tests. So it's going to be very common for someone to say, under some condition, so under our baseline condition of operations, we got a confidence interval for our performance data of this. It's this confidence interval goes from 0 to 0.5. We also happen to run in our real world system, our simulation or whatever, an alternative case where we ran it with a very different operational modes. Instead of doing a first in, first out queue, we did a last in, first out queue or something like that. And so I can then generate performance data for that alternative case and generate a confidence interval for that. If those two confidence intervals do not overlap, then without even asking for the raw data to run into a two sample t-test, I can conclude that those two conditions have performances which are significantly different from a statistical point of view. So just simply seeing that two confidence intervals do not overlap, I can conclude that the p-value of a two sample t-test with those two populations or data from those two populations are significantly different. So, right, so that's what I'll show you this graphically here. The other thing is a lot of times when people plot data for you, they don't plot confidence intervals, they plot standard errors. And so that's just, just the default or whatever. Sometimes people plot standard errors. And so, and standard error is actually, another reason why people plot them is if your data are independent, but are not normally distributed, you still are allowed to plot a standard error. Standard error only requires independence to plot it. Confidence intervals require the assumption of normality. So a lot of times the people also just plot standard errors to be conservative. That's the reason why standard errors is kind of the default. If you've given a standard error on a plot, then you can easily estimate the half width if you're willing to assume normality. And so when you do that by just taking the standard error, the mean that they've plotted, so the formula doesn't matter here, it'll just be the plot of this, and you multiply it by the critical t-value that corresponds to the confidence level that you want. Now, for a 0.05 confidence level, the critical t-value for a high degree of freedom, so with a lot of data, is about 2. That number, 1.96, I said you should probably remember that number. That is basically the critical t-value for 0.05 is your alpha, when the degree of freedom, so the number of data, is like more than 20 or something like that. It ends up converging to about 1.96. And so basically you double the standard error. If somebody plots standard error and you're wondering, these two bar plots, and I guess, let me see if I think I have a graph of this. So yeah, so here, I've got somebody plotted for me. I've got a control and a treatment. And so this was a pharmaceutical trial, and they were able to test enzyme activity under one drug, control, placebo, and another drug where it's the actual drug that they're interested in. And when I look at this, I look and they've written out that they've plotted the mean plus or minus the standard error for n equals 5. And so they got 5 samples here, 5 samples here. This is the mean, that's the standard error. This is the mean, that's the standard error. Initially, when you look at that, you say, it looks like the control has a higher enzyme activity than the treatment. So it looks like the treatment is making an effect. But then if you remember that the standard error, if you double it, it becomes the confidence interval, then this goes up about to here. This one goes down about to here. And now these two clearly overlap. So from looking at these data, even though it might look like there's a trend where the treatment is better than the control, statistically speaking, I can't say anything about this because the confidence intervals overlap. And so when the confidence intervals overlap, I have to do a formal statistical test. I have to do a 2-sample t-test on these data. I just have to. If these were confidence intervals and not standard errors, though, I can see that they don't overlap. There's daylight in between them. You can do the record test or something like, with the teenagers, or you slide something in between them. You can do that right here. And then that sort of ensures that these definitely separated. So if these were confidence intervals, then I could say, a 2-sample t-test would say that these are statistically different. That treatment is having an effect. And the effect size is roughly this. And so I could say that, but because they're standard errors, I can't because the confidence intervals overlap. Questions on that? So one of the beautiful things about confidence intervals being visualized is they very quickly allow you to evaluate the significance of data. This is also why we don't plot point estimates. If you just plotted the means here, then you would immediately say, the treatment works. But once you see the variance there, and then think about the confidence intervals, you see that this could happen randomly by chance, even if there was no effect. All right. So I'm going to skip that guy there. All right. So so I mentioned here that you can also estimate quantiles. So this is just me writing that thing out. So if I give you a confidence interval, I've effectively given you an estimate of the mean, which is just the midpoint of the confidence interval. If I give you the confidence interval, I also can give you the half width. It's just the length of the confidence interval divided by 2. And I also give you the standard deviation. So if I give you the confidence interval, you can estimate the mean, the half width, and the standard deviation. Given the mean and the standard deviation, you can estimate the whole distribution. And from that whole distribution, you can ask all sorts of interesting questions related to percentiles, related to whatever, because you have the whole CDF. So you can estimate an entire CDF from a confidence interval, so long as we assume normality, which we probably should, because you can't do confidence intervals unless you assume normality. So I give you a confidence interval, I am implicitly giving you a CDF of the distribution. And that CDF is it's just a normal CDF where you throw in the mean and the standard deviation you get from the confidence interval. Okay, questions on that? All right, and so now I've mentioned confidence intervals and I've mentioned quantiles as the other point estimator. Confidence intervals also apply to quantiles, and this is really hard to wrap your mind around because it's just percentiles all over the place. So when someone asks me for like the 85th percentile speed, I don't just give them a speed back. I need to give them a confidence interval, like a 95% confidence interval of the 85th percentile speed. So that's like a lot of percentiles in one sentence there. But it's but if you think about it, it makes sense because every time you run the simulation, you might get a different estimate of the 85th percentile speed. And so really what I need is to say, well, based on the 10 simulation runs I gave, I think the population's 85th percentile is within this interval. That's kind of what the confidence interval is there. And so how do I define a half width on a percentile? And so the way you do that is when the number of replications is sufficiently large, this here is a formula that you can use for the half width of a percentile in terms of ranking in the ordering. And so this might make more sense down here. If you've asked me for the P percentile, I then use that as the center of my confidence interval for the percentile. And then I subtract off of it this thing, which is going to be a number less than 1. And that will give me a lower bound on the P. And then I'll add it, and that'll give me an upper bound on the P. So then when I sort my data, so I've got my sorted data in this top row here, I've got their ranks in the bottom row. So it's just the order in this position there. 800, that is, in this case, I think I asked for the 80th percentile here. So 800, that is our estimate of the 80th percentile. But if we want to put a confidence interval around that, a 95% confidence interval around that, then I can plug in into this thing, the 1.96, that corresponds to the 95th part, the 5% alpha. I can then say, well, that needs to go actually from 78% to 82%. So for me to give you a confidence interval of the 80th percentile, I need to look in my rankings and give you the number that occurs at the 78th percentile in my ranking up to the 82nd percentile in my ranking. So that goes from, in this case, 188.96 up to 256.79. And that's my confidence interval there. So the point estimate of the 80th percentile of whatever this data is, is 212.03, but the 95th percentile confidence interval of the 80th percentile is this interval here. Are there questions about that? I know that's a lot. There's a lot of percentile stuff going around there. It's a lot of uncertainty here. It's just a mouthful to go through there. But it should hopefully make sense. Any point estimator, a natural question is to ask for the interval estimate of it, because we don't trust point estimates, because point estimates don't tell us about the uncertainty that comes from sampling randomly from simulations or from the real world. All right, questions about that? All right, so the last thing I want to cover here, and then we'll kick the rest of it to next time, is the prediction interval, which I already mentioned a little bit. So the confidence interval is a measure of risk. It's how risky is using this estimate of the mean. The prediction interval the confidence interval is a measure of error. It's how much error might I get if I use this mean. The prediction interval, as we say, is a measure of risk. And so the prediction interval looks a little bit like the confidence interval. I still take my sample mean, I add in this critical t-value, but now I scale it by something else. So instead of scaling it by the standard error of the mean, I scale it by this thing here, which is the standard deviation times square root of 1 plus 1 over n. So if this were just 1 over n, then this would, like I say, would look just like the confidence interval. So what this does is it effectively estimates the distribution of this whole measure that we're measuring here based on the little bit of data that we've gathered from the simulation. So as n goes to infinity, then this t value effectively goes to a z value. And so this thing here, as you take more and more samples, as n goes to infinity, this prediction interval goes to theta, the real mean, plus or minus the critical z value times the real standard deviation. So this here is effectively giving you a box where you're saying where are most of the values going to come in any given run of the simulation. But given that our simulation, if we only run a few samples, then we have we have a noisy estimate of the mean. So our mean is centered in the wrong place. So that adds additional variance. So this captures the variance in the distribution just naturally from the population, plus the additional variance that just comes from the sampling process because it run a finite number of samples. So that's what the prediction interval gives us, is it's instead of estimating the mean, it's estimating where is a large fraction, like 95% of the data. So the confidence interval, if I generate 100 confidence intervals, 95 of them will include the mean. Prediction interval, if I generate 100 prediction intervals, then I don't even want to say it that way. A prediction interval is meant to capture 95% of the simulation runs within it. It tells you about the real spread. All right, so I have to maybe stop things there. So let me just do jump to the final attendance question. And we'll pick up over after the weekend. So the question here is what hypothetical values are represented in a confidence interval? The t-test rejected ones or the t-test not rejected ones? So basically I'm looking for rejected or not rejected. So the question there, again, a confidence interval is a representation of a t-test. The values inside a confidence interval, are they the hypotheses that are rejected by the t-test, or are they the hypotheses that are not rejected by the t-test? So is the confidence interval associated with the not rejected or the rejected hypotheses? And that's all I've got for you. So if you have any questions, feel free to chat with me after. Otherwise, I will see you next week. And you should have your feedback on the modeling reports as soon as I finish the last half. Let me just think. No questions online? If not, then I will go ahead and end the meeting here in just a moment. And have a good weekend.